If you on announcements, I posted this announcement here that gives you the info on the final. This Tuesday night at 7 p.m., that's December 8th, 7 p.m., LSA 191 is where you're going. We'll all meet there. I'm going to put up, what I'm going to put is a list of practice problems from your workbook to help you study. And then all the web work is still open from the whole semester. That's all good practice. If you want to come look over your hour exams, those are available. So office hours the rest of the week. Or if you look, I'm going to have some type of availability on Monday and Tuesday also during finals week. So I'll decide that and put that, either let you know Friday or put that up as an announcement when you can find me for kind of office hours study session. I won't have anything planned, but you can come and ask questions and work together in your studying. Okay? Questions on the final exam. It covers most of what we did all semester. Again, look for that. The main thing will be this problem list. I'll have a list of practice problems throughout the whole workbook that will help you focus your studying. Good? Okay. So let's look at web work. Those due today. Number 3 is one to talk about. So I put a note on Blackboard about this. Hopefully you found that to help you with this one, because I know that it's a little hard to conceive what's going on. But so you have a plane. Let's try that again. Wow. Okay, so and then you have a steep mountain like this. And this one, mine is at a 74-degree angle, so that this angle is 74 degrees. It rises 3,400 feet, so that means the height of the mountain is 3,400 feet, like this. Okay, and then it says the cable is to be installed at a point 800 feet from the base to the top of the mountain. Okay, so from the base of the mountain is like where you would start climbing it. This is the base. That's the base of the mountain. So 800 feet away, out here, is where we're going to put the loading station. Okay, and then we're going to extend the cable in a straight line up to the top. So this is 800 feet. And they want to know the length of the cable that you need to do that. So call that capital L. This is your cable here, from here to here. This is the mountain. Okay, so the triangle problems we dealt. So all this adjacent, hypotenuse, opposite stuff for triangles is always about right triangles. So this triangle right here, using the side of the mountain and the cable and the 800 feet, that's not going to be. We're not going to be able to use our sine, cosine, and tangent relationships. So we need a right triangle. So a right triangle then is going to involve then dropping a perpendicular here. And that actually gives us 2 right triangles. So there's that one with the cable. And then you also have this right triangle here, which may be important. It will be important because that's the angle that we have, right? So if we want to find the length of this the cable here, and we know this is 3,400 feet, so either we're going to need this whole length down here, or we're going to need an angle in that triangle. So what I see is let's get that whole length on there. How are we going to get this whole length down here? So this length right here. How can we get that length? We don't have an angle though. So we don't have this angle. So maybe are you looking at cosine of this, the blue triangle? Yeah, so what will the cosine of the blue triangle get for us? It'll get us this adjacent. So this is the adjacent side for that angle 74, right? So I'll call it A for adjacent. So that right there is the adjacent side for the triangle that's in the mountain that has that angle of 74 degrees. And actually we know that this is 3400. So what we have the opposite here, and we want the adjacent. So we use tangent, right? So tangent of 74 is going to be our opposite over adjacent. So we have to solve for A, and then once we have A, then we could get this whole distance here, and then we don't even need trig anymore, right? Because we've got two sides to this big triangle, and we get the third using the Pythagorean theorem. So this is going to be A times tangent 74 equals 3400. So therefore A equals 3400 divided by tan 74. Okay, so then this length here, the whole length of the base of the red triangle is going to be the 800 plus the adjacent side that we just found. So this is going to be 800 plus 3400 over tangent 74 degrees. And then we're home free because we got this leg and we got this leg, and we can get L is going to be square root of 3400 squared plus that thing squared. Questions on this problem? Doesn't make sense. It's so easy when I do it, right? So can you make all those connections and do that yourself? Here we go. I don't know, maybe this one? Okay, so identities. Let me cruise through some of these here. So this is going to be, number one, is going to be sine times. So tangent is sine over cosine. So our first strategy for these was what? Write everything in terms of sine and cosine. So then we're going to get sine squared over cosine. So we can kind of start looking at the list here and seeing what does that simplify into anything. Well, not tangent, not cosine. Secant times cosecant, no. What about this? 1 minus cosine squared over cosine. It's got the over cosine. So sine squared, does it equal 1 minus cosine squared? Yeah, that's just changing the Pythagorean identity around, right? So if you have the Pythagorean identity, which is sine x squared plus cosine x squared equals 1, then you could solve for sine squared x, or sine x squared. It would be 1 minus cosine squared. You could also solve for cosine squared. It'd be 1 minus sine squared. So in this case, if we solve for sine squared, it'd be 1 minus cosine squared. So there it is. So that one's D. Okay. 2. Yuck, right? A little bit of work to do. So what did I say? Everything's already changed into sine and cosine. So another strategy is add fractions with a common denominator. So our common denominator here is going to be 1 minus sine times cosine. All right, so what do we have to multiply top and bottom by here to get that? Cosine, right? Cosine top and bottom. So it's going to be, we're going to get cosine squared x. And then the other one, we have to multiply top and bottom by 1 minus sine. So when we do that, we're going to get squared. And then that whole thing is going to be over cosine x times 1 minus sine x. That's the first step. So I did a common denominator of cosine times 1 minus sine, and then I added the fractions. Okay, and so now we're going to multiply this out here. There's going to be 3 terms, right? It's going to be cosine squared x plus 1 minus 2 sine x plus sine squared all over our common denominator. So remember the third strategy. So the first strategy is change everything into sine and cosine when that helps. Second strategy, possible strategy, is add fractions. Use a common denominator, add fractions. Third strategy, look for to use known identities, right, that we know. So in the numerator, do you see anything? Look, there's a cosine squared here and plus sine squared equals 1, right? That equals 1. So in the numerator, we get 2 minus 2 sine x, which equals 2 times 1 minus sine x. And what was our denominator? Cosine times 1 minus sine x. What can we do now? Goes away, right? 1 minus sine x, common factor to the top and bottom, goes away, and we get 2 over cosine x. Well, 1 over cosine x is, by definition, secant. So really we have 2 times secant x. So this right here is equal to 2 secant x. That's an identity. It's true for all angle measures, right? So no matter what angle measure you put into that, that equation holds true. That's what we call an identity. Took us a lot of work to get there. That's going to be E. All right, this one's easy. What is secant? Secant is 1 over cosine. So really what we have here is sine over cosine. Tangent. Really we just have sine over cosine here. That's tangent. So it's A. These two are going to take more work. So I'll leave. I think we've done enough there. We're down to what, B and C. So again, select for 5. Change everything to sine and cosine. That'll make 2 fractions. Then add fractions with a common denominator. Then look for known identities to make simplifications. And other algebra, right? Other algebra. Same thing with this. Make 2 fractions and subtract the fractions with a common denominator. Okay. Questions on identities?
This is what you talked about in class.
Yes.
What do you plan on uploading the class video?
It was up last night, just kind of later. It was up at like 9:30 or 10ish. Is that right? No, maybe I didn't. That was a different class. I'll get it up. Yeah. Last chance. Questions on identities. Okay, so let's talk about vectors. So vectors, we need our trig, and we need our trig triangles. We need lots. trig is really important when it comes to vectors, so that's why we're doing it now. So first let's talk about what are vectors. And to talk about what are vectors, you have to talk about what are scalars. So vectors versus scalars. So a scalar is a quantity. So remember we said this course is all about quantities, right? Quantities are measurable attributes of objects. You've got an object, anything you can measure about it, we consider a quantity. Volume, temperature, distance, speed, okay? These are quantities. So quantities that just have magnitude but don't have an associated direction are called scalars. Okay, so what are some examples of scalars? What are some examples of quantities that don't have an associated direction with them? You can think of one? What's that?
Time.
She said time. Does the quantity of time have an associated direction in three-dimensional space? No, that's good. Scalar, so time is a scalar. What else? What's that?
Weight.
Weight. Okay, so actually weight is a force, and there's a direction of force for weight. But something similar to weight would be a scalar. Mass. Okay, so mass wouldn't have direction, but weight actually does because it's a force. Okay, other things. So temperature doesn't have direction. Mass we talked about. Time elapsed. Okay. Volume is another one. Doesn't have direction. Area. Okay, doesn't have direction associated with it. Okay, vectors then are measurable attributes of objects that also have an associated direction. So they have both. They have an amount, they have a magnitude, and they have a direction associated with them. Okay, what's an example of that?
Weight.
Weight. Okay, force. All right, so force. So not only is there the amount of force that say I'm pushing on this table. All right, there's an amount of force which I'm pushing, but I'm also pushing on the table in a certain direction. All right, if I use the same amount of force, but pull it up, that's a different value because the direction is different. Okay, so force. Okay, momentum. So your momentum is always has a certain direction associated with it. Okay, so now displacement is a change in position. So if I say I go 12 meters, that doesn't tell the whole story, right? I'm going to go 12 meters, but I'm going to go 12 meters, say from here to where. There's lots of ways I can go 12 meters. I can go 12 meters towards and out that door. I could go 12 meters up. I could go 12 meters that way and out the window. Okay? So displacement then gives us a change in position. It's a distance along with a direction. So then just the distance then is a scalar without the associated direction. Distance is a scalar. Displacement then has the associated direction with it. It's our change in position. So displacement has distance, but then it also has direction. It has both. Distance is just only how far. So similar to that is velocity. Okay, velocity, how fast, but also in what direction. That's what we mean by velocity. So then the associated scalar would just be speed, just how fast, regardless of direction. So this is why you can have a negative velocity. A negative velocity, what is in the opposite direction of whatever you called positive direction. So if I call a positive speed this way, the negative speed is whenever I'm going in the opposite direction of that direction that I called positive. But speed is always positive. It's always just how fast, no matter what direction you're in. So that's a scalar. Okay, doesn't make sense. So vectors now we're taking quantities just like we talked about all semester, and then we're saying certain ones have an associated direction with them, and those we call vectors. Okay, so how do we represent them? We represent them visually with arrows. So it's kind of obvious. The direction of the arrow then points in the vector's direction, right? So we say vector is a quantity with direction. So whatever direction the arrow is pointing, that's the vector's direction. And then the length, however we draw the length, it then corresponds to the magnitude. So if these were all vectors for the same type of quantity, say displacement, say these are all displacement vectors, meaning change in position, which one then had the greatest change in position? 1, 2, 3, or 4? 2. So and it's kind of a relative thing. So maybe that's 10 miles, all right? Or maybe that's half of a millimeter. But if these are all in the same illustration, then we know, like, so if this is 10 miles, then this is something around 5 miles, okay? And this may be 2 miles or 1.5 miles. So it's kind of a relative thing, right? So when you have vectors in an illustration or diagram, the longer the vector, the greater the magnitude of that, and then proportionally, right? Proportionally. Okay, so then what we call then vectors have a tip and a tail. So the tail is like the back end, and then the tip is the direction of pointing in the direction of the vector. Okay, and then symbolically, vectors are represented by a letter that's bold like this, or especially if you're writing by hand, you want to do it put a little arrow above it. And also people do like a half arrow. It means the same thing. So you could do this. Like that. And that symbol then is encompassing both the magnitude, how much, and direction. Which direction? Okay, so the polar representation, what we call polar representation of a vector, is representing vectors, sorry, that says polar representation, just as we've defined them, a magnitude and a direction. Okay, so the way that we then use direction is we say things like 45 degrees north of east, or 6 degrees west of north. Or 79 degrees south of east. So what does that mean? So it means that, so east, right? So east is this direction here. So it's 45 degrees north of east, then we're going to sweep up 45 degrees in the northerly direction. And that's going to be the direction 45 degrees north of east. So that first one there is something like this. So that's 45 degrees. So that same direction could also be expressed as 45 degrees east of south. So no, east, what is it? What could be? East of north. Okay, so here's north. So I could have also said that was 45 degrees east of north. And that would represent the same direction. Okay, so for these 4 vectors right here, I want you to just estimate the direction and use one of these constructs or one of these phrases to do it. So like if you were to describe the vector v, use this north, south, east, west language along with degrees to estimate the direction of v, and then same thing, a, and then we'll call this vector, say, c, and we'll call this one d. Okay, so estimate all of those, and there may be different answers. Okay, there may be different answers for these. So C is kind of like what we already did, right? So C, this is like, we don't have to do that one. 45 degrees north of east would be the direction, would be an estimate. Maybe it's a little bit more, maybe it's 50. Okay, so maybe C is 50. Just an estimate, right? So you're just eyeballing this to get the hang of this way of expressing direction. Okay, so work on V, A, and D. V, A, and D. Go. And let's say these are displacement vectors, and V is 7 kilometers. Then I want you to also estimate the magnitudes of these vectors relative to V being 7 kilometers. Suggestion. So what would we say for the direction of this? 50 degrees north of west. Does it work? Yep. A little bit more than 45. So 50 degrees north of west. Okay? A. So first of all, magnitude of A then. If V is 7, maybe 14. Looks like that's about twice as long, right? 14. Okay? Direction? 10 degrees west of south. Does it work? 10 degrees west of south. Yep. Anyone have something different? If it were 10 degrees west of south, it would also be 80 degrees south of west. We already did that one. Okay, last one here. What would you say the magnitude of that is? Would you estimate? 10. Something greater than 7, less than 14. So 10 is good. Direction? $30 degrees south of east. Does it work? Yep. Questions on this? This is polar representation. Polar representation means like it's kind of aligns with what we think about as vectors as a direction and a magnitude. Okay, a direction and a magnitude separately. So that's called polar representation. Okay, so a vector has a direction and a magnitude, but it doesn't have a distinct location. Okay, it doesn't have a distinct location. Okay, so 5 people move, starting at different places and times, but all go the exact same distance, heading the exact same direction. So there's the first, second, third, fourth, fifth. Okay? So since their direction is the same and their change in position, their distance is the same, so they're all the same vector. D1 equals D2 equals D3 equals D4 equals D5. So so what we say, vectors are mobile. Vectors are mobile. Once you have a set direction and magnitude, you can move that vector around. You can move it and apply it in different places, and it maintains the value, the what the vector is. Okay, so these are all just, you say they're all just vector D. They're just all vector D. Okay, now there's another way to express a vector. So if this point is, say, 2.3, comma, I don't know, 1.4, and let's call that point P. And then the tip is point Q, and that's at, say, 0.7, 0.7, 3.1. So there's another way to express vector D. We can also express it this way, as extending from a starting point, the tail, to the tip. So if you put the arrow over like that, like PQ, like that, that also expresses this vector D. So to remember, which is the tip and which is the tail, it's just by your arrow that you've drawn above, right? So P is the tail or the starting point, and Q is the tip or the final point. So from P to Q is defining that vector, from P to Q. Okay, and so then this brings us to another way to express, besides the polar representation, there's what's called the component representation. Component representation is looking at so since it's like from P to Q, it's looking at from P to Q, what does X do? X goes from 2.3 to 0.7. So what is our change in X? So in the component way of looking at it is, let's consider the change in X and the change in Y. And that's what we did in the first week of class, or the first couple weeks of class. We looked at changes. And this makes sense with the fact that the vector is mobile, right? It doesn't matter where it is, but the associated change in X and change in Y is going to stay the same. So how would we calculate the change in X? What is the change in X for vector PQ? What is the change in X from point P to point Q? That will be the X component of vector D, or vector PQ. So final minus initial, right? So 0.7 minus 2.3 is negative 1.6. And that's how much X changes from P to Q, right? It goes negative 1.6. We'll see this on the next slide. And then change in Y. It's final minus initial. 3.1 minus 1.4, I think is 1.7. All right? So that's the same no matter where you place the vector. So over here, what's our change in X from here to here? It's still negative 1.6, the amount of change in X. And then the change in Y is still positive 1.7. So the coordinates of the starting, the tail can change, right? The coordinates of the tail can change, but the amount of change from the tail to the tip stays the same no matter where you place the vector. So this is now what we call the component representation of the vector, which gives a change in X and the change in Y, as opposed to giving the magnitude and the direction of the vector. Okay, so adding vectors. So adding vectors, you place the arrows tip to tail. So like since vectors are mobile, I can move A so that its tail is at the tip of B. And then the sum is its results. It's the single vector that results in the same outcome as the original vectors applied in succession. So if I were to apply vector B and then apply vector A, that would be the same as what single vector? Do you see it? What single vector would that be the same as? So like there, right? That single vector, which we call B plus A, has the same overall effect, starting at the tail of B and ending at the tip of A. So that's the sum, B plus A. So what if you change the order? So what if I did A plus B? Do you get the same vector? Yeah, you get the exact same vector. So A plus B equals B plus A. You see, they have the same magnitude, same direction. They're just in different places, right? Okay, so this is what we talked about before, vector components. So vectors can be expressed as changes of their horizontal and vertical components. We saw that. So this vector u, then, and there's vector v. And so I'm showing that vector u is really representing a change in x of -1. It's going to the left, negative. To get from the tail to the tip would require a horizontal change of -1 and a vertical change of +2. Okay, so then we can express this vector as -1, 2. So this is the more common way to express vectors. So there's the polar form, but the more common way to express vectors is in component form, which expresses the changes in each coordinate. Change in x, change in y. Okay, so v is a change of x of +4 to the right, and a change in y of -2 or 2 down. So v is 4, -2. So in order to add, if we wanted to add two vectors, what's going to be more convenient? Is it going to be the polar form or the component form? It's going to be more convenient for adding. All right, so I want to add v plus u. So v plus u. So if v means we go 4 to the right and then u means we go 1 back, then what's the overall result of that? 3 to the right. Okay, and if we went 2 down and then 2 back up, the overall result of that is 0. So the component form is very, very convenient for adding vectors because all you have to do is add the changes, right? You just add the change in x, you add the change in y, and you get your resulting change in x and your resulting change in y. In this case would be 3, 0. Okay, and so again, what we said this before, the length of the arrow represents the magnitude of the vector, and so we want to find the magnitude of each vector. Find the magnitude of each vector if it's the length of the vector. So the easiest one there is v plus u. What's the magnitude of v plus u? 3, right? So it's going from this point -3 point something. Anyway, so it's what? Its change in x is 3. Changes y is 0. That means the total magnitude of that vector is 3. So that one's easy. So now what about these that aren't v and u, which are not either horizontal? So if you got a horizontal vector or a vertical vector, magnitude is easy. It's just if it's a horizontal vector, it's the change in x. If it's a vertical vector, it's just the change in y. But what about if it's not horizontal or vertical? So you should be able to figure that out. So we said this one's easy. And so then to represent the magnitude, you would have what's like absolute value bars. Sometimes you also see double absolute value bars for vectors. That means the exact same thing. So whether you see double bars around a vector or single bars around a vector, that's signifying we just want the magnitude of it. We don't care about the direction anymore. Just how much, what, how much stuff, or how. Okay, so we said that was 3. What about the magnitude of u? The magnitude of u. How are we going to find the magnitude of u? You've got that the change in x is -1, the change in y is 2. Yeah, what you have to see is that those components are forming a right triangle, right? The components of the vector form a right triangle by which you can get the magnitude of the actual vector. So this leg right here is how long for this triangle? Yeah, so at -1, but so just for finding the magnitude, we think of it as 1, okay? And then 2. Magnitude of u then is 2? Square root of 5, right? Square root of 1 squared plus 2 squared. V square, again, think of a triangle. This leg is 2, this leg is, V is square root of 20. Magnitude. Questions on that? Okay, so let's put it all together here. Force vectors A and B are applied at the origin. Find the component representation of each vector, and then find a vector that gives the resultant force at the point, meaning what's one vector that would be equivalent to both of these vectors acting, pulling on the ground at this point. Okay, and we want to give that resultant force vector both in component and polar form. Okay, so this is a matter of finding the resultant vector is a matter of what operation with regards to A and B? So what would we do to vectors A and B to figure out, okay, what's the one vector that's, yeah, we're just going to add them, right? We're just going to add A and B together, and that's going to represent what the resultant force is at the origin here of this thing. So if we're adding, so we can think about that as putting it, if we do A plus B, we can take B and move it up here so that its tail is at the tip of A. Something like that. Vectors are mobile, right? So that's vector B. So we're expecting a resultant force something like this. After we do the math, we're expecting the resultant A plus B to be a vector like that. And we don't have time to do it. But just briefly, how are we going to get, so in order to add, what do we say? We want component form to add, right? We want to add the change in x for A plus the change in x for B because it's very convenient to do it that way. Because if you're just looking at, we have polar form here, right? So we just have, so who knows what direction this is, right? Who knows what the angle is, and who knows how long this is? That's why we want component form. So we need each of A and B in component form. How are we going to get A and B in component form? Right. So we have a right triangle like this. And so here's our x component of A. So the magnitude of A is 4, and it's an angle of 40 degrees. So what is this component of A right there? Cosine of 40. Is it cosine of 40? So that's as fraction of a radius, right? So if the length of A was our radius, then cosine 40 would be that fraction of whatever radius is. So if we want kilonewtons, how are we going to get how many kilonewtons that is? Times 4, right? So there's our x component of A, and our y component of A will be 4 sine 40. So there's our component form of A. 4 cosine 40, 4 sine 40. We're going to do that for B. And then in order to get the resultant force vector, what do? Just add together the x changes and add together the y changes. Add the component of x for A to the component of x for B. And the component of B or y for A plus the component of y for B. And that will give us this vector A plus B in component form, right? It'll give us a resulting change in x, a resulting change in y. Use the Pythagorean theorem then on those components to get the magnitude of the force of A plus B. Okay, so no quiz, no more